Let's start. Today only 6 participants, students. Okay, strange. All right, we start now. Okay, let's continue. So we are now working with, so we discussed the problem of Friedman, as we usually say, Friedman cosmology or Friedman-Lemaitre cosmology. And one of the problem, this is flatness problem. So why the universe, the space in the universe is flat, and exactly omega, I need to put here omega 0 equal 1. So, and this problem which we need to solve, this is one of the important problem of Friedman cosmology. The second one also called also important in sense that, so we call it problem of monopoles. So as you know that when we speak about so when we speak about magnet, we understand that magnet has 2 poles. So this is, and it doesn't matter if you cut it, in any case, you will have 2 poles. But it was also some idea which was suggested by Maxwell that can be, and later can be the idea from electromagnetic theories that can one pole which called monopole exist, and magnetic monopole. So in principle, this is maybe looks like a strange suggestion, but some we speak about, for example, unified theory, which try to, and this is dream of the physicists, to build the unified theory, like a great or giant unified theory, such a way that the theory consider together all interactions. So, and such kind of theories, they predict the possibility of existence of such kind of object, the magnetic monopole. We don't observe such kind of object. So, and there is a question. It means that if, for example, such a theory predict the existence of this monopole, it means that they are not right, they are not good, and need to refuse this theories. Or maybe this is really we can't observe it due to the fact that it's really very rare objects. So to consider this is also one of the problem for Friedman cosmology. To consider this in more detail, considers the energy which correspond to each process, which is related to the connection of interaction of fundamental physical interactions. For example, I will start to speak about the energy of electroweak interaction. So it means, in principle, we understand that we have 4 fundamental interactions. This is electromagnetic, this is weak, this is strong, and this is gravitational interaction. So 4 of them. And the idea is that if we will go in the time, in the beginning of the universe, of the appearance of the universe, when universe were very hot and correspond to high energy, it means that such a time the interaction can be joined together due to the fact that during the evolution of universe, the temperature went down. As a result, each of the next interaction which correspond to the some energy started to go out and to be independently. So this is the main idea. We will speak, if we will speak about energy of electroweak fraction. So this is it means that we consider the case when electromagnetic and weak interaction are together, so joined in one interaction. There is such suggestions that it corresponds from 1 tera electron volt. Sometimes there is a idea that it can be 100 giga electron volt, but in principle we can use a high limit of this energy. And what is tera electron volt? So 1 tera electron volt, this is 10 and 12 electron volt. So if we will recalculate for the corresponding temperature, we just can, as an estimation, we can use this is energy, electroweak, divide on the Boltzmann constant. So if you will put here the energy in constant Boltzmann constant, so we'll obtain approximately 10 and 16. So it means that if we have a condition correspond to the matter with a certain kind of temperature, we can suspect that magnetic it's also the idea to look to see which cosmological time it will correspond in the universe. So and to do this, we need to use our expression for again what we have for now. We have only Friedmann cosmology. In any case, we can use it, suggesting that we are on the scale more than larger than the Planck scale, and we can use expression which we obtained through the solution of Einstein equation. In the first, we need to find the relation between the scale effect between temperature and cosmological time. To do it, we can find in the first the relation between temperature and scale factor, which is for us will be useful. So and for this we just need to write what the energy density. Energy density. This is a constant. How call it? Radiative constant alpha T in force. So alpha, this is just a constant which we can find, which we know. So if we will, so for example, we can write this for the present time, and also we can write the energy density for as a function of T, or for example, redshift in force as a function on redshift. So if we will compare these two, we know that also we know from our previous calculations that energy density, this is energy density 0, so here we need to, A0 I can forget, force, in force. So, and since we know that we have a relation between scale factor and redshift like this, so we can write that it will be epsilon 0, 1 plus z in force. So this is expression for the energy density, which we can write through the redshift, which is also correspond to the distance of the object with the time. If we will put it in find the ratio between epsilon z and epsilon 0, so we can write that alpha, sorry, alpha, right, I don't want that, alpha t in force, this is z equal, and on the right side we will put exactly the expression of energy density through the expressed through the redshift, so epsilon 0, 1 plus z in force. So and epsilon 0, this is alpha t 0 force. So from this we obtain the important expression between for the temperature. So T equal T0, 1 plus Z. This expression can tell us how temperature change due to the change of the redshift. And we understand that if we go in future, or in, sorry, in past, so Z tend to, let's consider to infinity like this. Of course, it will be not infinity in principle, but I just want to show that this can be a very huge number of redshift. And we can see that T also not 12 to, okay, to infinity like this. So we come to the idea of the whole universe in the past time. Also, we can, in principle, since we know this relation between scale factor and redshift, we can also write that T equal T0, and instead of 1 plus Z, we will put 1 divided on A. Again, you can see that if we go to the past, it means that A tends to 0 and T tends to infinity. Now let's find the relation between temperature and cosmological time. For this, we can use the dependence of scale factor on cosmological time for radiative stage. We just obtained it before. Yeah, this one. I will put here some side. So, okay. So A equal 3 square root omega R0, H0, 1 divided on 2 square root of T. So this is relation, this is for radiative stage. And we discussed already that when we, since universe has a three stage, general stage, when we go to the past, really very past time, early time of the universe, we need to use this expression. So everything, omega r0, h0, constant. If we will put everything here, so I will not spend time to show this, we will obtain that a approximately this square root of t, and t in tenths. There is a number, but it doesn't matter. From this, we can obtain since T0. So this is temperature T0. This is temperature of cosmic microwave background for the present time. When we speak about emission, we speak exactly about cosmic microwave background. So these photons which we have after the whole time of the universe. And let's put it in this expression for the temperature. So we in this case obtain that it will be and this temperature equal for now 2.7 Kelvin. So approximately, if we will put here, so I can know with accuracy some in front, I can approximately write that it will be 10 in tenths divided on square root of t. So this is relation between temperature of the matter, which we speak about, emission principle, relativistic matter, and cosmological time. Here we and from this, of course, we can write that otherwise t approximately this is 10 in 20 t squared. So okay, this is the point. And here the temperature here we put in Kelvin. Just to, and finally we obtain the dimension of time in seconds. So for this, so this is relation, so t, this is cosmological time. So in this case, if we will make a very simple estimation, so for example, for the energy of electricity temperature, approximately 10/16 Kelvin, we will immediately obtain that it will correspond to the cosmological time. Let's put it here like this. So it will be 10/20 divided. So you can see that with huge number we are working. It's approximately 10 minus 12 seconds. So it means that when universe, the age of universe was less than 1 picosecond, in this time we can suggest that it existed only 3 fundamental interactions. So T less than T electroweak with only 3 fundamental interaction. This is gravitational interaction, strong, and electroweak. So this is in principle when we speak about electroweak interaction. So we have some proof of this. For example, predict that the mass of Z boson on 13%, we set, for example, the mass of double V plus minus bosons. And it was discovered some times ago when the theory of electroweak interaction was built together with Weinberg, Salam on collider. It was really proved that exactly what was predicted in theory correspond to the nuclear experiments. So this is this we know, but you know, this idea that as well as we have joint electromagnetic interaction, we can build electroweak interaction, and if we will logically continue, so in principle we can suggest that maybe we can build some unified theory. It's called grand unified theory. Grand unified theory. Shortly we can use. And suggested that joint grand unified theory, the energy which correspond of this theory, this is approximately 10, 12, 10, 13 tera electron volt. It means that when we reach this energy, so the strong and electroweak interaction join together, and it's represent one interaction. It's understandable that it should be realized so for really high temperature, and we can estimate it since again we can yeah, precise. E good divide on Boltzmann constant. So if we put constant Boltzmann, then they good, so we will obtain 10 in 20 Kelvin. So this is really huge temperature, but doesn't matter. We can use, of course, energy, but for us temperature is useful because we can immediately to obtain the estimation of cosmological time. So it will be let's put here, so 10 in 20s, and here 10 36, so this is 10 minus 36 seconds. So we can tell that we can say that when cosmological time was so small, so we are really not far from the Planck time, we can suggest that it was realized grand unified interaction, which corresponds to grand unified theory. So all three interaction work together. In principle, we can, of course, when we speak, you know, sometimes we say that the universe, this laboratory for the poor people. For the poor people, when we speak about, in this case, about poor people, it means humanity, because really, if we would like to investigate what's happened for such kind of energy, so it's we need to build really huge collider. For example, the hadronic, the great hadronic collider, which was built to find the Higgs boson. So the energy Large Hadron Collider. So multimatter large L Hadron Collider. So which is large Hadron Collider. This is really great instrument. So I visited, it was this collider some years ago, and it was built to prove the existence of Higgs particle, which is important for to finalize the standard nuclear theory. And for example, Higgs boson explain why, for example, double V plus minus, because double V plus minus boson, which are responsible for the electroweak interaction. So this is this particle, say, I'll call it. So, if not in English, переносчики взаимодействия. Переносчики. I don't know how to say it in English. Переносчики. Same is important particle to exchange for the electromagnetic interaction. For this double V plus minus Z neutral bosons, they are responsible for electroweak interaction. So boson, Higgs boson, explain why double plus minus Z boson has a mass. So this particle was predicted in the theory and was proved due to working of this Large Hadron Collider, which is located on the boundary between Switzerland and France. The length of this collider, this historical collider, is approximately, does I remember, 26 okay, meter, I will write meter. So, and energy which reached on this collider, this is like 14 tera electron volt. So, and you understand that it's really far than the value which we would like to obtain for the grand unified theory like this. For example, if we will continue to use our technology and we would like to reach this energy linearly, you know, just to build using our technology to build a greater, larger collider, we can really simple to calculate that for this energy, we need to multiply on 10 and 12. So it means that for wood need to build the collider with a length of 18 centimeter. And so this is approximately 1%. So we need to build a collider with a distance to the nearest star, which is impossible. So in this case, and this is one of the problem of verification of the theory, because when we speak about high, because we really now limited by our technology to check it, to prove and to verify which theory is better. Because there are many theories, string theory and multidimensional theories. So, and they concur with each other. And one is the possibility to for the verification, this is exactly cosmology. So this is why we speak, why we say that universe is a laboratory for the poor people, for the poor humanity, in the sense that we don't have a really huge technology for now to make a direct experiment to verify theory. Okay, so also, so this is such a point which I would like to mark, that if we agree with the point that it really could be like this, that for the higher energy, the interaction joined with each other. In principle, I like to present some scheme of this idea of the hot universe. So we can, when we speak, and is even much more so, for example, the idea of Einstein, and he wanted to build such a theory, but he didn't succeed, as we understand, because it's not simple. This is to build the theory of everything, so-called theory of everything. So the theory of everything, I will put now scheme. It means theory of everything. So it means that all four interactions were joined together, including gravitational. And it's really it's a good idea, of course, but it's really complicated to realize it, if in principle possible, because we need to join together the interaction which is working on the huge scale with the interaction which are working on the small scales. And this is a problem, because in this case, of course, we need to use a quantum gravity like this. And this is really complicated problem, which we didn't succeed yet. I mean, I say, of course, about scientific community. So if you speak about, let's call it theory, everything. So it will correspond scale. So if we will put here the first the energy in tera electron volt, temperature in Kelvin, and T seconds. So we can write here that it should be 10, 16, this is energy. 10, 32, we found this. I just put here the Planck scale of time and corresponding or Planck scale of energy and corresponding to temperature. So you can simply recalculate it if we know what we found before in the first lectures. So and time, this is 1 minus 33. In principle, when we, and this is one of the possibility to avoid the cosmological singularity, to speak about quantum appearing of universe. So this is point to avoid the situation when scale factor equals 0. You can write in your conspects that to avoid the cosmological singularity, we need to speak about quantum appearing of universe. So in this case, we limited by Planck scale and Planck time axis. So in principle, we can speak that, okay, when we speak about birthday of the universe, so we can speak about Planck scale. And we can suggest that when it was appearing, so we all four were joined together, including gravitational. When a universe expands, so as a result, the temperature down, and in the first gravitational interaction out became free, you can say gravitational interaction, and this. So what about the next stage? This is the moment of grand unified theory. When three, so in this time here, all three interactions were together, but on this moment, which correspond to the energy right here, 10 and 12, temperature 1028, which we found, time 10 minus 36. So it was important event. The strong interaction became free, but still we have together weak and electromagnetic interaction. So, and again, for some moment, so here we can write electroweak. When this energy was corresponded to 1 tera-electron volt, 1016 temperature Kelvin, and time 10 minus 12. So the weak interaction became free and electromagnetic. And finally, we have what we have, the 4 fundamental interactions. So this is an idea. In principle, in this time, when we speak about and the theory predicted that on this time, for example, can be realized some phase transition, which usually, you know, we also meet even in our life some phase transition when you have water, and the water can become as ice or and otherwise separate. So this is 3 kinds of the water which can exist corresponding to some temperature. So we can speak about phase transition. Such a kind, not called such a kind, but something similar, we can, it's predicted can exist when on this moment, when strong interaction became free, and it suggested that it can be okay, yes. So it can be spontaneous symmetry breaking, which can create some special structure. And for example, some theory predicted structure can appear. For example, when it was passing from this moment T good, suggested appearing from the theory, unified theory, which called the string theory of elementary particles. It can appear at one-dimensional object, which called as a cosmic string. Cosmic strings. So this is such a kind of break-in which create the defect of the space, which looks like cosmic strings. 2-dimensional, this is domain false. And 0D, 0-dimensional, so it means point, this can be magnetic monopoles. So some theory predicted that it should be appearing such a kind of defects, And if we will observe it, it means that this theory is right, so we can use it, even in despite of the situations that can't directly to make an experiment for such a kind of energy. So in this case, really cosmology important to build the fundamental physical theories. But there is a problem, because about cosmic strings, all time I remember that it was predicted that when Planck telescope or WMAP, COBE telescope, we discussed this in the previous lectures, was working to investigate cosmic microwave background. It was suggested that if really such a kind of space defect exists, it should be recognized on the CMB maps, because it should be like a straight line on the distribution of cosmic background. And it was suspected to find it, but unfortunately not COBE, the next not WMAP, the next not Planck didn't found such kind of structure. Of course, theoreticians who are working with a string theory all time say that okay, maybe they recalculate everything and predict that maybe we need to reach much more accuracy to find such a kind of structure. So they don't give up and say that okay, for now we can't found it, but not because the theory is wrong, but because we didn't reach yet accuracy which correspond to possibility to find them. Of course, it's also possibility to change the theory, since for this limit we can't find such a kind of structure. So you need to work with the theory to put it corresponding to the observational data. This is the point. So okay, if we speak, so if some theory also predicts that magnetic monopole can appear exactly on this stage. So, and if we will means that it should correspond to this energy, and we can in principle estimate which concentration of magnetic monopole should be on this time, and later, for example, for the present time. So if we will estimate it, we can concentration of monopoles for, let's consider for the T good. So in principle, we can estimate very loosely, in the sense that we can find it as a number of the particles on the volume, which is has a scale the C D good. So it means that so C on T, this is some dimension of the scale in one direction and another direction. So we have to. This is what we can do, and in the cube. If we will put here where C, this is speed of light. So if we will put all values, we will find that the concentration should be incredibly huge. So this is 1075 centimeter minus 3. And it's one of the problem, because it's really tells that we need to discover, we need to for this of course time to see what we will have. For now we need to calculate. If we'll it's interesting to compare with the energy density of the gamma quants of the photons for this time. But in the first, we can calculate the energy density on this time. So we just need to multiply E good on n monopole, which correspond to this time. So this is 10, 12, this I can simply write. And since we put here 10 and 12, this is tera electron volt centimeter cube. So together it will be 1087 tera electron volt centimeter cube. If we will calculate the energy density of gamma quant, you will understand later why I decided to do it. So this is alpha T for good, and we know alpha, we know T good, so it will be approximately 1087. You can check it, centimeter and cube. So it means that on the time correspond T good, the energy density of gamma quant, again, gamma quants in this case, they appearing due to even for this, due to some many reaction which can appear due to interaction of the particles. And in this time we can speak about quark in free state and gluons. So it will be 10 in tenths epsilon monopole. So in principle, what we can see from this, that from this on this stage, the gamma quant is much more important in sense of the total energy density than monopoles. But if we will go in the future, so since we know that this is not good because it looks like a mater. Let's put it monopole. Okay, mon. Here also. Okay, okay. So if we will remember that when we found before epsilon radiation, I will put here gamma, just this is also radiation, but just to show that it's really energetic photons. So we speak when energetic photons, we speak about gamma quant. So an epsilon it's equal proportional to scale factor. So it means that we can find when epsilon gamma became equal epsilon monopole. So it will be exactly, it will be not exactly, but it will be for the scale factor, which equal 10 in tens. So it means then if we will go from time and the space will expand in 10 in tens, finally the monopole will dominate respect to emission, to radiation, to photons. So and we can even calculate when it will be. So if we find temperature, so this is T good A, gamma M, so it will be 1028 divided on 10 tenths, so it will 18 Kelvin. And this allows us to obtain the cosmological time gamma M, which is 12 divided on t squared gamma m. So if we will 10 16 seconds from the moment of quantum appearing of the universe. Time, the monopole should be dominated part of the matter in universe. But it's strange that we don't see them, don't observe, we don't observe them. So, and it tells that we need to exclude the theory which predict monopole and leave only the theories which doesn't predict the existence of this monopole, or we need to explain why we don't see them. So this is such a kind of problem of magnetic monopole. So the third problem, this is horizon problem. Horizon problem. This is also one of the important problem of the cosmology, which need be solved, because we can discover that, for example, if we will calculate the cosmological horizon for the present time of our region, if you can observe this exactly. So approximately we can estimate, doesn't matter the number in front, so like a C multiplied on the edge of the universe. This is 10 to 88 centimeters, so we found it before. If we want to see at which scale of our casual region, okay. Which so I will remind that, when we speak about cosmological horizon, it means that this is principal region which allow us to information about object. So, and we found much more precise expression before, but in principle we can use like this C on T0 to estimate this region. So, and if the galaxy or some object out of this region, and we are here. Okay, this is observer. It's better to put here I. So here we have observer, and if some object is outside of this sphere, we in principle can't observe it for now, because the old time of the universe is not enough that electromagnetic emission will reach us during this time. So, and if we look, and this region called, we can call casual region. And if we will look in причинно связанную область, if we look which size this region had in the, for example, the Planck scale. So I want to find this. I will keep here 0 just to remark that this corresponds to our region which we observe for now, and let's go in the past for the Planck time. So in this case, we'll have we need to, if we will suggest the cosmological horizon also change, or the distance, the distances between objects changed due to scale factor. So we again put this cosmological principle LH0. So we found this H. Okay, I remember through temperature, so I can write it through temperature. Okay. I remember just that scale factor I can express through the temperature, the ratio of temperature. T Planck on LH0. So, and this is for the Planck temperature, remember, so this is 10 minus 32 on 10, 28. And it means that this is approximately 10 minus 4 centimeter. So this is the scale of our casual region for the Planck. Let's now consider, but which to estimate the cosmological horizon on the Planck time, and calculate that cosmological horizon. So we just need to put C multiply on T Planck. So this is multiply on 10 in tens, and Planck, this is on minus 40. So it means 10 minus 32 centimeters. What we obtained? We obtained that if we will find the ratio of the T Planck, approximately 10 and 28. Or if we will now found ratio of the volume, cube, so we just need to put in cube. It will be 10 in 4. So what it means? It means that if we will consider the Planck scale, on the Planck scale, we will have this number of non-causal region. Non-causal regions. So it means that, for example, just schematically to write, this is the schematically the scale of our causal region for the Planck scale. But inside this region, we will have, since we have, since we have the cosmological horizon many small, smallest, many, this is this number, which can't connect with each other. It means that, for example, if something happened in this region, or some transition, phase transitions, the temperature falling down, or otherwise something happened, this region will not know anything about all this. This region too and this region too, so we can put it in. They will live all of them with their life, so and will not know what's happened in another one. But this is exactly, let's put it, this is LH0 on T Planck. So, but in this case, there is equation, but why, if in the Planck scale, in this early time, we had so many non-causal regions, why now we have, which is a matter in everything, which is homogeneous and isotropical. So it should be that inside of this scale, for now, we could have in this case many regions which, with different conditions, principal different conditions. So this this point contradicts to cosmological principle. So we can, as a conclusion, to write that this on contradicts the cosmological principle, which we observe, which we know, which came to us. So this is homogeneous and isotropical distribution, and this is one of the really important problems, especially this one. Two of the problems, these problems, horizon problem and flatness problem. So this is already enough to see how we can solve the problem, to find some solution to solve this problem. There are also in principle, also schematically, we can also to discover this horizon problem, that if you will, for example, build the dependence of distance, okay, some distance as a function of t. So for the horizon, for the cosmological horizon, it will be some line, okay, straight line. But we know that on radiation stage, the scale factor proportional to square root of t, so it will be like this. And so this is horizon, and this is the distance between, for example, two particles, two galaxies, two particles. So and this corresponds to the case at a proportional square root of t. So, and what we can see, so if even from this simple consideration, we also can see that if we are we're on some time in the past, we can see the distance between two particles here more than the scale of horizon. We already can see even in advance that the cosmological horizon for some period should be less than the distance between two particles, because the law is different, the change of the time. And it means that really we need to have in the past non-causal regions, and with the numbers we could see that even a lot of causal regions. So, for example, for the future, yes. So we can see that horizon became bigger and larger than the distance between particles, so everything is okay. Also, there are also an entropy problem. So why its entropy is so huge, and also so I don't have the time to speak about this. Also, there is a problem. It was a problem with seeds. Primary, okay, let's call it disturbances. So it means that if we speak about universe on the Planck or around Planck scale, we need to, when we speak about Friedman cosmology, we don't speak about quantum physics, because it's you understand that in Friedman cosmology, you just go to the case when A equals 0. So, and in this case, there is also problem how we can grow up the structure of the universe. What is the primary seeds of the matter, which finally create the large-scale structure of the universe? So it's understandable that only considers the Einstein equation and Friedman cosmology is not enough. So we need to use something else. But what is much more important with these problems? How we can solve this problem? I can see 10 minutes. I will start. So this is the model of inflation. Inflation stage of universe. So inflation stage, it means that, and we already have solution. You remember this solution and also the solution for lambda term. It means that we can use the equation E minus epsilon. Again, P is pressure, epsilon is the density energy. So and we know for this case, we will have the Friedman-Lemaitre equation. Doesn't matter, forget about the k equals 0, so in the sense that we can consider the k equals 0 for simplicity for now. So we can we can keep the summand, which is related only with lambda term. But I will put here the index I, so it will be lambda term which correspond to inflation stage. So remember that it's divided on 3, and since lambda has a dimension of the length, maybe I need to put here c square like this. So this is the first equation, and the second equation for velocity. Okay, a point divided on a square equal lambda I c squared divided on 3. It means that since a point divided on a, this is Hubble parameter. I will put here Hubble parameter for inflation. So it will be square root lambda I multiply on c. And we know that in this case, we have a scale factor which proportional to E hi multiply on t. So we can see that really, and we remember that the scale factor change exponentially. So why is this such kind of solution also called inflation? Because inflation is a process for which the speed of changing of some value is a proportional of this value. So it means that the inflation, this is exactly that a point lambda I on 3 ta. So you can see that the speed of changing of the velocity, yes, proportional to this value, to this factor. The same procedure in economy. So inflation, when the speed of increasing of the money proportional to the numbers of the money. So it means that you print much more money, and in this case, the cost of the product became even more expensive, and you again need to print new money, and like finally you have inflation and the economy falling down. So in economy they also use this term. Okay, I have 5 minutes. So the idea is such a way that let's suggest that we can switch on the exponential change of the scale factor in some moment of time. Let's call it Ti. And this inflation starts from this time and to reach T finish. So let's put it T finish. So we switch on this inflation for some time. By the way, yes, and also there is another problem in Friedman cosmology, because you need to extend the space from the really micro scale, for example, quantum scale, to the macro scale. And it looks like the time is not sure that it's enough for the 13 billion years to succeed with this. So really to reach the scale which we have now. It's also one of the points that need some switch on some very fast evolution at the time in the history of the universe. So this we can switch on inflation. In this case, we can consider the change of scale factor such a way that so we will have inflation, and let's put here A inflation. So EHI on some moment which started from Ti. So it means that this is exactly inflation which we want to switch on. Sorry. Before this, we just need to put the formula for radiation stage T less Ti. Check message. And for the after inflation, we will have HI T finish minus Ti. And so this is exactly the multiplier which tell us how huge became now the scales. But after this, we need to also to remember that later it will continue to expand as corresponding to the radiative stage for T more than Tf. So it means that this corresponds to AI. This is beginning of inflation. And finish correspond to A T finish, which is so when we reach this, so it will be HI TF minus TI. So this is the end of inflation. And we can estimate, so in the point, in this all inflation theory, this series was suggested in 1980, so it was a great cosmologist, Alan Wood, Vlenkin, so and also many people was working with this inflation stage, and it was great idea. You know, they have different point to ask how much we need, how long we need to use this inflation stage to solve the problem of Friedman cosmology. So it's understandable that if you will, it's, you know, if folder number, so it should be E in some n. So one of the equation, which n we need to use to solve all problems. For example, if we will can estimate, if we will now simply, of course, the theory is not so simple because it has to include the quantum effects and like this, but just, you know, to have as well of this. So if we switch on T inflation, what we can use? We can use, for example, T good current unification theory. So, and we know the time, this is minus 36 seconds. HI is just 1 divided on T good. This is approximately 36 seconds minus 1. It means that if you want to obtain this number of n, so we can look here, this is exactly the same. So this is HITF, because HI on TI, it doesn't important. So okay, let's to just recognize HITI. So this is will be unity. We need to understand which time we need to put. So usually for now, this inflation theory says that the finish should be 10 minus 34. In this case, since we have here HI 36 multiply minus 34, so you will have final 100. So it's principle, it's enough if the space will expand in so in let's here to put again TF divided on TI as a E 100, or if you go to 10, this is 33. So for now, consider that this is enough. This number is enough to succeed with solving of the problem of Friedman cosmology. So it means that it's enough to switch on inflation for the this time, for the number of the time. So it's very shortly, but as a result, we can see that we can solve all the problem of Friedman cosmology. And I have also problem because so we have only 2 lectures, and which we decided to finalize on Wednesday. Maybe I will very quickly to speak about this problem, and we have 2 lectures and to speak what is inflation, and finalize and to speak about hot model of universe and dark matter, finalize everything. So for now it's okay. Let's see. We have some questions. I'm sorry, I need to rush. I sense that not now, I mean to give lectures because we don't have enough time. So If you have some question, you can ask me now. No questions. Or you don't understand what about we spoke? No. Tell me something. Are you here?
Yes. Yeah, we have. Maybe not.
You know, you don't have a questions. You know, there is just a joke about Stalin. When some call to Stalin, Stalin take the phone and say, no, 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 and repeat it 10 times. No. And for example, Beria asked him, but Osip Vissarionovich, once he said yes. I said, ask, but you all time said no, 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 but only one yes. What was question that you said yes? And he said, he asked me, can I hear him well? And I said yes. So this is just responding talk. Okay. No any questions. Okay. So I received I will look later your answer, your home tasks. So everything is okay. The questions I will prepare for and will send you later. So if no any questions, in this case I close Zoom and see you on Wednesday. Which time? Which time we will meet? Please remind me. Is it? I understand right that we will meet with each other on Wednesday. This yes.
Wednesday time.
Time.
Well, and
Third and fifth pairs.
So then, but which time? The time of the third pair. This is 12. 12?
Yes, that's no. This is
12.
third pair. So 12
and
and after that 15, 20.
15th. Oh, okay. Thank you. Okay, so good day for you and see you on Wednesday.
thanks for